Good morning everyone. I am Anurag Singh. As you know, I study in JYOTI classes. I am student of class 12 Kendriya Vidyalaya. Today I am going to teach you all what I have learned in the class today about the chapter number 5 in physics class 12 magnetism and matter. We will discuss all the important topic which will come in exam as we have studied it from exam point of view. So I hope this will be helpful. First, magnetism. What is magnetism? What are the properties of magnet and what causes magnetism? All the important topics. Cause of magnetism. As we know, everything have a cause, so magnetism also have cause due to which it is applied, and it is applied to the materials. Properties of magnet. Every material has its own properties and its own specialties, and magnet also has its own properties. So we will learn about properties of magnet in this. Magnetic field. As we know that charge has its own field, and magnet is also type of charge, as it magnet also conduct current when passed through in material or circular coil, which it induces current in the coil. So here is magnetic field, and there was also one topic in electric charge known as electric field lines. So here will also be one topic, magnetic field lines. Next, we will study about magnetic dipole. And then magnetic dipole moment. As we know that there was electric moment of the dipole, so here also we will study about the magnetic dipole moment. These are all the topics which are likely to come in exam, so we will study very carefully. And there are two derivations in this chapter. Important derivation to torque on magnetic dipole placed in magnetic field. Torque on magnetic dipole placed in magnetic field. This is the first derivation which will come in exam from this chapter. And the other one is potential energy stored in magnet on moving in magnetic field. This is the topic. When a magnet will move in the magnetic field, some energy will be stored in the magnet in the form of potential energy. So these two derivations are the derivation which will come in exam from this chapter. Other than these two, there are no derivation in this chapter. So I note down this. And one important law, there is named Curious law. Curious law is likely to come in numerical question. It will give the value of find Curious law, derive Curious law, express Curious law. What is Curious law? This type of question. Going to look. we are going to do the derivation first. Before the derivation, we will learn about magnetic dipole. As in the derivation, it will come in work. I think you all know about electric dipole. It's the same as magnetic electric dipole. There was two charges separated by small distance. Here, the charge of the magnitude of either pole. There are, as we know, in magnet there are two poles. In magnetic dipole, we will only take one pole. You can choose the north pole or the south pole. The magnitude of either pole of magnet separated by a small distance. This is the definition of magnetic dipole. The magnitude of either pole of magnet, any one pole separated by a small distance. South, north distance between them. Magnetic dipole. And there is another one, magnetic dipole moment. It is the important topic which will come in numericals and derivation. Magnetic dipole moment. Magnetic dipole moment is also the same. The here it will be the pole of magnet. The unlike poles or the unlike poles of magnet separated by a small distance. This will be the magnetic dipole. In the magnitude will be written in this one. The magnitude of either pole. The magnitude of either pole of magnet separated by the magnetic length of magnet. First we learn about what is magnetic length and what is geo length. This is the actual length of magnet L, and the distance between the pole south to north is called magnetic length. If we have given in the numerical the magnetic length and we have to find the geo length, we can write it as magnetic length equals to 5 by 6 geo length. If we have given geographical length and we have to find magnetic length to put it in the numerical, we will do this. This is the derivation to find magnetic length if we have given the geo length. Hope you write it down. Now, if we have learned this topic, now we are moving towards the derivation, because this will come in derivation. Use of this will come in derivation. First, we will draw magnetic field lines. Magnetic field lines will be going like this. The name of the derivation will be torque on magnetic dipole placed in magnetic field. Torque on magnetic dipole on magnetic field. So by reading this sentence, we all understand that this is the magnetic field. A magnet will be placed in here like this, south, north. Magnetic dipole, it is given magnetic dipole, so the length will be like this, 12, it will move toward this south pole. We all know that this is a magnet. North will go toward this direction. The force applied on this will be mb, small m into magnetic field mb, and south will go to this direction. It will move toward this direction mb, small m into b. Small m into b. The angle we can given by the given figure. We will do some construction by a dotted line. This angle will be theta. This will be 90 degree. This will A B C. Triangle ABC. Magnet dipole will be applied. This pole will go towards the magnetic along the direction of magnetic field, and this pole will go opposite direction of magnetic field. As we know that what is torque equals to mb into AC. This is the value sin theta. This is perpendicular. This is base. This is hypotenuse. Theta. Sin theta equals to perpendicular by base. Sin theta p by b, perpendicular by base. Perpendicular is AC and base is BC. The base is BC, 12. The length 12. Sin theta equals to perpendicular by hypotenuse. P by H, hypotenuse is 2L. Sin theta equals to AC by 2L. Now we can write here torque equals to mb into AC. As this will go in this direction, this will go in this direction. Suppose this is magnet, torque applied this direction and torque applied this direction. The magnet will move toward this direction. So torque will be mb into AC. mb is the force applied on magnet along the direction of the magnetic pole. We can write AC equals to sin theta into 2L or 2L sin theta. Now we will put it here. Torque equals to will be small mb. We are talking about magnetic force m into b, small mb. In the place of AC, we can put 2L sin theta. 2L sin theta. Before only now, small time ago, we have learned the magnetic dipole moment. I hope you all remembered magnetic dipole moment. M equals to small m into 2L. This vector sign will not come on 2 as this is magnet. It is a scalar quantity. Only length, as length will have direction and A2 will not have direction. This is the formula of magnetic dipole moment. Magnetic dipole moment. So here it will be like mb into 2L sin theta. M and 2L can be written m into 2L b sin theta. Here will be b, here will be b, capital B. Torque will be m into b sin theta. This is the formula of torque applied This is the formula of torque applied on a bar magnet placed in a magnetic field. This is the derivation. We have obtained the direction. This is theta. If sine if theta equals to 90 degrees, MB sine 90 MB sine 0 degree MB torque equals, then torque will be equals to MB maximum torque applied on the bar magnet if theta will be equals to 0 degree. Remember it. When theta will be equals to 90 degree, angle will be equal to 90 degree, then torque will be equals to MB sine 90 degree, theta equals to 90, MB. We all know that sine 90 degree value will be 1. By mistake I have written sine 0 degree value 1. Now I confirm it. This will be the maximum torque applied on bar magnet in magnetic field. If the value of theta will be 90 degrees, the angle between the magnetic field lines and bar magnet will become 90 perpendicular. Then there will be maximum torque applied on the bar magnet. If theta equals to 0 degree, torque will be MB sine 0 degree, torque will be MB into 0. Torque will be 0. This will be the minimum. This will be the minimum torque if theta will be equal to 0 degree. If it will be the if this is the magnet direction of magnetic field line, magnet will be also in direction this. Then the angle between them will be 0 as both in same direction. So there will be a minimum torque applied on the magnet. Write down this derivation. This is the first important derivation of the chapter, and there will be one last derivation. These magnetic field lines. The second derivation which will come in exam, the last derivation, potential energy stored in the bar magnet, moving in the magnetic field. By reading the statement, we understand that when a bar magnet will move in the magnetic field, the magnetic direction of magnetic field, when a bar magnet will move forward and backward, some amount of energy will be stored in the magnet in the form of potential energy. This will be the derivation to find out the potential energy that is stored in that magnet. First we will draw the diagram. As if we did not draw the diagram, marks will be cut. As diagram is important, or the invigilator will not be able to understand what we have written as theta 1 and theta 2. You will understand what is theta 1, theta 2 after I draw the diagram. This is magnetic field. This is not. They are going in this direction. Magnet placed, bar magnet south, north, angle theta moving forward and backward. We know that on doing this, some amount of work will be done. By moving the magnet, we are doing some amount of work. So as we know from earlier classes, the formula of work force into S, displacement W equals to F into small distance in the magnetic field only. We are moving the magnet in the magnetic field only. So the distance covered will be very small, like this. So diagram will be like this. This is the work for small place. So we will write dW. Force. This is the force applied. So we can also write force into displacement. Force. What is the other name of force into displacement? Torque. So we will write here dW equals to torque into d theta. Theta, as there is theta distance moved, so the distance ds will be d theta. Integrating both sides. First we will put the value of torque from the above derivation. From the before derivation, we know the value of torque. In the question we will put it dW equals to mb sin theta into d theta. mb sin theta into d theta. Now we will integrate it. Small amount of work done in this, then the total amount of work done in the magnetic field by the magnet. So we will do integration. If there was total amount of work done and we have to find out small amount, then we have to do differentiation. But now we have got the small amount and we have to find all the total amount. We will do integration. Integrating both sides. Integrating both sides. Integration dW equals to integration mb sin theta theta 1 to theta 2 d theta. The value of theta 1 will be pi by 2, theta 2 will be 0. Remember the value of theta 1. First the magnet is in this direction, angle 90 degree. On moving this, we will get theta 2 0 degree, angle 0 degree. Integrating, we get W equals to MB will come outside, theta 1 से theta 2 sin theta into d theta. On integrating MB sin theta, we will get minus cos theta by theta 1 to theta 2. Minus sign will come outside, minus mb cos theta, theta 1 to theta 2, cos upper limit minus lower limit. This is the application of integration we have learned. Work minus mb inside the bracket cos theta 2 minus cos theta 1, cos theta 2 minus, in the place of theta we will put the first upper limit minus then again lower limit. So this will be minus mb cos theta 2 minus cos theta 1. Now we will put, now we can see here, this we can also do, or also it's your choice. What we can do, like minus sign inside cos theta 1 minus cos theta 2. The sign will change, as if minus will be multiplied, it will become minus, and minus minus plus, so it will come forward. Now putting the value of theta 1 and theta 2, we will get W equals to MB cos theta 1 is pi by 2 cos pi by 2 minus cos 0, cos 90 minus cos 0 degree. Write down this part, we will rub it. cos 90 degree. सर वैल्यू ऑफ cos 90 क्या था? cos 90 का वैल्यू जीरो, और cos 0 का 0 1, cos 90 degree 0 minus cos 0 cos theta. Theta 2 will be theta, as we don't know the moment of theta 2. Here also will be cos theta. 0 minus cos theta, W equals to MB cos theta minus MB cos theta. This is the derivation of potential energy stored in magnet or moving on magnetic field. This will the a derivation which will come in exam of the both potential energy stored in the bar magnet or moving in magnetic field, and the other one the torque one. Write down it. Here will be theta 1 and the second angle will be theta 2, will be theta s. No, we will continuously keep moving the magnet. We will not place in a stationary direction, so it will not become zero. It will remain unchanged and unidentified, so it will remain theta. These are the two, and the other important formulas for exam numericals will be, in numerical there will be small formula combined together. So for not lagging your mind and for not we will complete all that small formula. Next topic, it will be small topics only for numerical. Magnetic force. Magnetic force. Magnetic force will be the force applied on the magnet placed in the magnetic field. Magnetic force is the force experienced by the materials when placed in a magnetic field. It will be given as, we know that magnetic field, the unit of magnetic field is B. B equals to mu naught. Mu naught is a permeability constant, relative permeability. Mu naught into Ni. Mu naught into Ni. I is current, N is number of turns in the coil or of magnet, equals to Ni. Magnetic force is given by H. It is also called magnetic intensity of magnetization. It is intensity. We can find intensity of magnetization also after this process. Ni, the value of Ni will be equals to H. Value of Ni will be equals to H. Remember it. So here we will get B equals to mu naught H. H will be equals to B by mu naught. B here. B will be magnetic field. Mu naught will be constant value 4 pi into 10 to the power minus 7. Mu naught value constant 4 pi into 10 to the power minus 7, and B will be equals to magnetic field. A value of H, we have derived magnetic force. In question we have to find the magnetic. If we have given the value of Ni and H, we will find the magnetic force easily. Now the another one, intensity of magnetization. Other formula, I have to draw it, and so here I will write. Intensity of magnetization. Intensity of magnetization. Intensity of magnetization. Intensity of magnetization can also be written at the magnetic field line at that point, as if magnetic field lines are placed in a single point connected, then there will be the amount of magnetic field will collide and magnetization will be hot, and by intensity of magnetization we can find the amount and the density of magnetic field and the power of magnetic field at that point, or of magnetic force. Intensity of magnetization, current equals to m by v. M will be magnetic dipole moment, v will be velocity of the magnetic field line. I equals to mv. We will remember this formula, rubbing it. Next formula important, susceptibility. Susceptibility is the ratio of intensity of magnetization by the magnetic force. The ratio of intensity of magnetization by magnetic force H, magnitude of magnetization I. The symbol of magnetic susceptibility will be Xm. Xm equals to I by H. This is the important formula which we have to remember for numerical purposes. Write it down. Susceptibility. Xm equals to I by H. I is intensity of magnetization, also other name the magnetic field lines deposited at a point or at a point in the magnetic field. H is magnetic force. Now we will the important question, the last important formula for numerical, Curious law. This law states that the intensity of magnetization, this law states that the intensity of magnetization is directly proportional to H, magnetic force I directly proportional to H, and inversely proportional to temperature T. I inversely proportional 1 by T. Law of magnetic intensity will be inversely proportional to T. Now we can complete both. We can write this like this: H by T directly proportional to H, inversely proportional to T. If the proportionality sign will be removed, then there will be a constant placed in the place like CH by T. C is the curious constant. Here it will be I by H equals to C by T. Before topic only we have learned the value of I by H will be Xm, also known as magnetic susceptibility. So by this relation we get that Xm equals to C by T. This is the Curious law. This is the Curious law, which is very important. If we have got I and H and C, we have to find. We can find by Xm using this thing. Paramagnetic. Now we will write some theory which I have learnt. I am going to rub it. Let me check. This is the last important topic of this chapter, types of magnet. Types of magnet. There are three types of magnet: paramagnetic, diamagnetic, ferromagnetic. Ferromagnetic. If diamagnetic, examples we can write: copper, diamagnetic, copper, diamagnetic, copper, nitrogen, silicon, copper, nitrogen, silicon. Ferromagnetic, iron, nickel, cobalt. Iron, nickel, cobalt. Iron, nickel, cobalt. And paramagnetic, aluminium, sodium, calcium, and also etc. These are the examples. Some example: if a diamagnetic substance will be kept in a magnetic field, magnetic field. If a diamagnetic substance will be kept in magnetic field, it will weakly repel the magnetic field coming towards its direction, passing from it. Weakly repel. It will weakly repel the magnetic field. The magnetic field coming in this direction will be weakly repelled by this diamagnetic. The property of diamagnet is when magnetic field passes through it, parallel to it, it will weakly repel the magnetic field lines. In case of paramagnetic, in magnetic field lines, if a paramagnetic substance will be kept, paramagnetic substance will be kept, it will weakly attract the magnetic field line towards itself. It will weakly attract. So when the magnetic field will be coming in this direction, it will get weakly attract. Magnetic field line get weakly attract toward the paramagnetic substance. This is the property of paramagnetic. And the diamagnetic, when diamagnetic substance, it will strongly attract. Diamagnetic will be weakly repel magnetic field. Paramagnetic will be weakly attract magnetic field. And this will be ferromagnetic. Ferromagnetic will strongly attract the magnetic field, not weakly repel or not weakly attract. Strongly, all the magnetic field line will be passing through it. Strongly attract. Example of ferromagnetic: iron, nickel, cobalt will strongly attract the magnetic field towards its direction, and it will make them pass through it. Diamagnetic: copper, nitrogen, silicon, it will weakly repel the magnetic field line coming towards its direction, small displacement. And paramagnetic strong, weakly attract. So some amount of magnetic field line will get attract to it. Properties of diamagnet. Properties diamagnet. Magnetic susceptibility, the topic we have studied before, the I by H. Magnetic susceptibility will be small negative value In case of diamagnetic, we can by column we can both all three we can write together only. Diamagnet, diamagnet, paramagnet, ferromagnet. In diamagnetic, the magnetic susceptibility Xm will be small negative value, Xm will be small negative value. In paramagnetic, Xm will be small positive value. Magnetic susceptibility will be small negative, magnetic susceptibility will be small positive, and here Xm magnetic susceptibility will be large positive, value, very large positive value. Here susceptibility, magnetic susceptibility doesn't change with change in temperature. Doesn't change with temperature. Here in case of diamagnetic, when temperature changes, the magnetic susceptibility will not change, it will remain constant, same at all temperature. In paramagnetic, on changing the temperature, Xm magnetic susceptibility, which is the symbol, will be inversely proportional to temperature. Xm will change. If temperature will be increased, magnetic susceptibility will be decreased. Xm will decrease, and if temperature will be decreased, magnetic susceptibility will increase. Hope you understand. And by this we can write the formula also. C by T, Curie's law, as we write before. And in ferromagnet, here Xm will be directly proportional to C by T minus T naught. This will be the relation between magnetic susceptibility and temperature. It will also change with increase. It will also decrease with. It is also inversely proportional to temperature. As this one important topic which I am going to write. When on increasing heat, the ferromagnetic substance break down and shows the property of paramagnetic substance. I have told on change in temperature, the ferromagnetic substance shows the property of paramagnetic substance. On increasing temperature, the susceptibility of paramagnetic substance on increasing temperature, the susceptibility of ferromagnetic substance will show the same as the property as the susceptibility of paramagnetic substance. This is important. Third point, mu r will be less than 1. Mu r in diamagnetic substance, mu r will be less than 1. Relative permeability will be less than 1. In paramagnetic substance, mu r will be more than 1. Mu r will be more than 1 relative permeability, and in the ferromagnetic substance, mu r will be very larger than 1, less than 1, more than 1, very larger than 1. Mu r is the relative permeability. Relative permeability. The property of diamagnet is also, when kept in non-uniform field, when kept in non-uniform magnetic field, the poles the pole move from stronger to weaker field. The pole move from stronger to weaker field. In paramagnetic, when kept in non-uniform field, the pole will move from weaker to stronger, and here in ferromagnetic also same, it will move from weaker to stronger. These are all the properties of type of magnet, which are three type of magnet: diamagnet, paramagnet, ferromagnet. Diamagnet will weakly repel the magnetic field and coming toward its direction. Paramagnet will weakly attract the magnetic field and coming toward its direction. And ferromagnetic will strongly attract the magnetic field and coming toward its direction. The properties will be: magnetic susceptibility will be small negative value for diamagnet, small positive value for paramagnet, and large positive value for ferromagnet. Susceptibility does not change with temperature in diamagnet, as on increasing temperature the magnetic susceptibility will remain constant. Susceptibility is inversely proportional to temperature in paramagnet. So increase in temperature the magnetic susceptibility will decrease, or decrease in temperature the magnetic susceptibility will increase. The derivation we have come before, that formula for magnetic susceptibility, we can use it in this for paramagnet substance, C by T, C, Curious law. This is also known as Curious law. And for ferromagnet also, this will be the relation between temperature, as on increasing the temperature the magnetic susceptibility of ferromagnet starts showing the properties of the magnetic susceptibility of paramagnet. This is the effect of temperature on ferromagnet. After certain temperature, the ferromagnet starts showing the properties of paramagnet in terms of magnetic susceptibility. And this is mu r. Mu r is relative permeability. If mu r will be less than 1 in diamagnet, more than 1 in paramagnet, and very larger than 1 in ferromagnet. And the last point we will write will be: when kept in non-uniform magnetic field in any direction, diamagnet will move from stronger to weaker point of the field. The stronger point will be near the magnet and weaker will be away from them. It will move away from the magnetic field, weaker point. It will if it will kept in non-uniform, it will move in towards the stronger magnetic field, and this will also show the same property. It will move toward the strong magnetic field. This is the end of the chapter. Hope you all like it. This is the chapter 5. Important topics I have learned for the exam point of view. Thank you. I am Anurag, studying in JYOTI classes of class 12 student. Thank you very much.